This is Lecture 7, Foundations of Statistical Inference. By the end of this lecture, you should be able to understand why it is difficult to make inferences from one sample, calculate a standard deviation, be familiar with the z-distribution, be familiar with the t-distribution, calculate a standard error of a sample mean, calculate a confidence interval around the mean of a sample distribution, calculate a confidence interval around a sample proportion, and be familiar with commonly used Greek symbols. Imagine I collected data on the percent of people living below $2 a day in less developed countries. In all, there were 124 LDCs in total. After I collected this data, I found the population mean, denoted by the Greek symbol mu, for this variable, which was 34.8. So on average, 34.8% of people in less developed countries live below $2 a day. It would be nice if we could always collect data on the entire population of cases that we are interested in. However, it is almost impossible to do so. Most of the time, we simply collect data on a subset of cases within a population. This subset of cases is called a sample. After we collect data on a sample, we use information from that sample and apply it to the population. So imagine that instead of collecting data on all cases, I took a random sample of 10 countries. For this sample, the sample mean, denoted by X bar, was 29.4. Based on this data, I would conclude that 29.4% of people in less developed countries live below $2 a day. Clearly, this value is not reflective of the true population mean of 34.8%, so our sample estimate has some error. In order to illustrate how far off a sample mean can be, I created 10 random samples from the dataset of the 124 less developed countries. The averages for the percent living below $2 a day variable range from 19.6% to 46.7%. As you can see, different samples can lead you to draw different conclusions about the true population mean. Clearly, these values are often not perfectly reflective of the true population mean of 34.8%. So once again, sample means often do not equal population means. This is a problem since we use sample means to make conclusions about population means. In the rest of this lecture, I'm going to show you how to make more appropriate estimates of a sample mean. But before I do that, I have to show you how to calculate a variable's variance and standard deviation. The variance and standard deviation of a variable tells us how often individual observations deviate from the mean of a variable. Recall that in a dispersed distribution, most observations lie far away from the mean, while in a clustered distribution, most observations lie close to the mean. The variance and standard deviation are just mathematical measures of exactly how often observations vary from the mean. A large variance and standard deviation means observations are dispersed from the mean, while a small variance and standard deviation means observations are clustered near the mean. These two graphs illustrate two distributions with the same mean, but one has a small variance and the other has a large variance. The variance for the entire population of a variable is denoted by the Greek letter sigma squared. The standard deviation for the entire population of a variable is denoted by the Greek letter sigma. The population variance for our percent living below $2 a day variable was 575.2, and the standard deviation was 24. I calculated these variables on my own. You do not need to know how to do this. Once again, we often do not work with an entire population of cases. Instead, we work with samples, which are a subset of cases from the population. So when we want to estimate the sample variance and standard deviation of a variable, we use the following equations. First, the sample variance, denoted by an S squared, is the sum of each observation minus the sample mean squared, and that value divided by the total number of observations minus 1. Second, the sample standard deviation, denoted by the letter S, is the square root of the sample variance. In order to calculate the sample variance, you start by taking the sample mean of your data. Recall that the mean is just the average of all the cases. So let's say we collected data on the percent of people living under $2 a day in 10 countries. Your overall mean of this data was 29.4. Then you subtract the sample mean, in this case 29.4, from each observation. So for country 1, you calculate 46.1 minus 29.4, which equals 16.7. For country 2, you calculate 60.4 minus 29.4, which equals 31. And you continue this process for each observation. Note that all we are doing is calculating how far each individual observation deviates from the mean of 29.4. Next, you take the values from step 2 and square them. So the calculation for the first observation would be 16.7 squared, which equals 278.9, and the calculation for the second observation would be 31 squared, or 961, and you continue this process for each observation. Note that we square the values to get rid of negative deviations. It is impossible for an observation to negatively deviate from its mean. Next, you add all the values from step 3 together. In this case, the value is 5,840.4. Then you take the value from step 4 and divide it by the number of observations minus 1. In this case, the number of observations was 10, so 10 minus 1 is 9. So the calculation is 5,840.4 divided by 9, which equals 648.9. So the variance for the percent living under $2 a day sample is 648.9. Note that all we are doing here is calculating the average deviation from the mean. We added all the deviations together and divided by the total number of observations minus 1. That is almost like calculating an average. Last, you take the square root of the variance to find the sample standard deviation. We take the square root because we squared the values in step 3. As a result, the values of the variable became much larger. So we take the square root to bring the number back to a more realistic level. In this case, the square root of 648.9 is 25.5. So our standard deviation for the percent living under $2 a day sample is 25.5. Now we can interpret the mean and standard deviation. We would say, on average, 29.4% of people in less developed countries live below $2 a day. However, in our sample, observations varied about 25.5% from the mean on average. Note that we always work with samples. As such, our sample standard deviation will not be the same as the population standard deviation. The population standard deviation will always be smaller than the sample standard deviation. Recall that the population standard deviation for the percent living under $2 a day was 24, while our sample standard deviation was 25.5. Now that I have shown you how to calculate a standard deviation, we will now talk about estimating the mean from a sample and applying it to the population. We are able to estimate a sample mean and confidently apply it to the population because of something called the central limit theorem. The central limit theorem tells us that if we collect an infinite amount of samples, let's say we take an infinite amount of samples of 1,000 observations each, 95% of the time, the sample means from each of those samples would be very close to the true population means. This is because the distribution of samples means is normally distributed. So just for a visual representation, here's a picture of a potential distribution of sample means. Imagine that this is the true mean here. 95% of the time, when I take a sample of 1,000 observations, the mean of that sample will be within 2 standard units of the true population mean. So even though our sample mean often will not equal the true population mean, the population mean and the sample mean will be very close to each other. Before I move on, I would like to talk a little bit more about normal distributions. Normal distributions have one mode, so they are unimodal, and they are shaped like a bell. Normal distributions are symmetrical, meaning that if you fold them in half, each half will have the exact same shape. In addition, the center of a normal distribution is the mean, median, and mode of the distribution. Next, 68% of the values of a normal distribution are within one standard unit from the mean. 95% of the values of a normal distribution are within 2 standard units of the mean, and 99% of the values of a normal distribution are within 3 standard units from the mean. Standard units take into account the standard deviation and sample size, which I will talk about soon. These characteristics mean that 68% of the time, a sample mean should be within plus or minus 1 standard unit of the true population mean, and 95% of the time, a sample mean should be within plus or minus 2 standard units of the true population mean, and 99% of the time, a sample mean should be within plus or minus 3 standard units of the true population mean. Using the concepts of the central limit theorem and the normal curve, statisticians developed 2 hypothetical distributions to use in statistical analysis, the z-distribution and the t-distribution. The z-distribution is a hypothetical normal curve that has a mean of 0 and a standard deviation of 1. You can take any values of any ratio level variable and mathematically transform them into z-scores. This allows us to analyze variables with small values, such as in the tens, and variables with large values, such as in the millions, on the same scale. I'm not going to teach you the equations necessary to transform the values of a variable onto the z-distribution. However, I will tell you that whenever you do take a variable's value and transform it into a z-score, the calculation for the mean of the variable will always result in a value of 0, and the calculation for the standard deviation of the variable will always result in a value of 1. This is because the z-distribution has a mean of 0 and a standard deviation of 1. In addition, recall that the z-distribution is a normal distribution, so 68% of the values are within 1 standard unit of the mean, 95% of the values are within 2 standard units from the mean, and 99.7% of all the values are within 3 standard units from the mean. Although the z-distribution is a useful tool, it does not take into account that some samples are small and some samples are large. With smaller samples, we have less confidence in our data because there is less information. With larger samples, we have more confidence in our data because there is more information. The t-distribution allows us to take into account differences in sample size when analyzing our data. The t-distribution is actually a set of distributions that account for sample size. The smaller the sample size, the larger the variance in the t-distribution. The larger the sample size is, the smaller the variance in the t-distribution. Here is a visual representation of t-distributions. The z-distribution has the smallest variance, so 95% of the time, the observations are really close to the mean. The t-distribution for a sample size of less than 30 has the largest variance, so 95% of the time the observations are very far away from the mean. And the t-distribution for a sample of 30 is moderate. The variance for it is moderate. So 95% of the time the observations are somewhat close to the mean. Now I'm going to show you how to use the t-distribution to estimate a population mean. To do this, we calculate a 95% confidence interval around a sample mean. The confidence interval allows us to take a low estimate of our mean and a high estimate of our mean. I will use the following data to demonstrate how to calculate a confidence interval for a sample mean. Imagine I collected data on the percent of people living below $2 a day in 10 less developed countries. The first step in calculating a confidence interval is to calculate the sample mean of the data. The mean of this data was 29.4. Next, you calculate the standard error of the sample mean. To do this, you take the sample standard deviation, which I showed you how to calculate earlier in the lecture, and divide the value by the square root of the number of observations. The sample standard deviation of this data set was 25.5, and the number of observations was 10. So 25.5 divided by the square root of 10 is 8.1. Next, we have to calculate something called the degrees of freedom. The degrees of freedom is the number of observations in our data set minus 1. So we had 10 observations. 10 minus 1 is 9. We use our degrees of freedom to find the value from the t-table that we use to calculate the confidence interval. You can find the t-table on page 146 in your textbook. On the left-hand column is your degree of freedom rows. There you will find the row that corresponds to the value of your degrees of freedom. If the value is not listed, you choose the closest lowest number. After you choose the right row, you must find the right column. The column headings tell you the percentage of cases under the top portion of the t-distribution curve. So for the 0.05 column, it is 0.05 or 5% in the upper part of the curve. Although the table only focuses on the top part of the curve, we want to know the area under both ends of the curve because we are calculating a lower boundary and an upper boundary. That means that if we are examining the area under the top and bottom of the curve, we would want to have 0.05 in the upper half and 0.05 in the lower half. If we add 0.05 plus 0.05, we have a total of 0.10 under the entire curve. So if we want a 95% confidence interval, we want 0.05 under the curve. So we would want to look at the 0.025 column as it indicates 0.025 in the upper end and in the lower end of the curve for a total of 0.05 under the entire curve. So we use the 0.025 column and the 9 row. The t-value that corresponds to the 0.025 column and the 9 row is 2.262. Note, from this point forward, you will always be required to use the 0.025 column for confidence intervals. So you should just make a note somewhere to use the 0.025 column for confidence intervals. Now we have all the information we need to calculate our confidence interval. The lower bound of the confidence interval is the sample mean minus the t-value times the standard error. So in this case, the calculation would be 29.4 minus 2.262 times 8.1, which equals 11.1. The upper bound of the confidence interval is the sample mean plus the t-value times the standard error. So in this case, the calculation would be 29.4 plus 2.262 times 8.1 for a value of 47.7. Now we can say that we have 95% confidence that the true mean of our variable lies between 11.1 and 47.7, or we can say that we have 95% confidence that the true mean of our variable is 29.4 plus or minus 18.3. Note that 18.3 is just the t-value multiplied by the standard error. Now we can calculate confidence intervals for proportions. We use proportions when working with responses to certain types of survey questions. So for example, imagine we collected data on how many people support candidate 1 versus candidate 2. We had 100 respondents and 52 supported candidate 1 and 48 supported candidate 2. We want to make an estimate of how many people supported candidate 1. First, we would calculate the proportion for individuals who supported candidate 1. The calculation for the proportion P is the number of cases in a category divided by the total number of cases. So in this example, 52 respondents said they supported candidate 1, and there were 100 total respondents. So 52 divided by 100 is 0.52. We also have to calculate a value Q, which is the number of respondents who did not support candidate 1. The calculation for Q is simply 1 minus P, or 1 minus 0.52, which is 0.48. Next, we calculate the standard error of the sample proportion. The standard error of the sample proportion is the square root of P times Q, and that value divided by the square root of the number of observations. So in this case, the standard error of the sample proportion is the square root of 0.52 times 0.48, and that value divided by the square root of 100, which is 0.05. Next, we have to calculate the degrees of freedom to find our t-statistic. Recall that the degrees of freedom is the number of observations minus 1. So in this case, we had 100 observations, so 100 minus 1 is 99. Going to table 6.4 in your textbook, you have to look for the 99 row. Since there is no 99 row, you look for the closest lowest one, which is 90. Then we look at the 0.025 column, since we want a 95% confidence interval. The t-value associated with the 90 row and the 0.025 column is 1.987. Now we have all the information we need to calculate the lower bound of our confidence interval. The calculation is the proportion minus t times the standard error. So in this case, the calculation would be 0.52 minus 1.987 times 0.05, or 0.42. Next, we calculate the upper bound. The calculation is the proportion plus t times the standard error. So in this case, the calculation would be 0.52 plus 1.987 times 0.05, or 0.62. So we conclude that we have 95% confidence that the true proportion of people who support candidate 1 is between 0.42 and 0.62. Or we could say that we have 95% confidence that the true proportion of people who support candidate 1 is 0.52 plus or minus 0.10. 0.10 is simply the t-value times the standard error.